Brian Conrad from Stanford University, and he will give a talk on pseudo-reductive groups, titled Introduction to Pseudo-Reductive.
Okay, thank you very much. Oops. Let me start from the back. So Gopal Prasad and I will be giving 4 talks. I'll give the first 2, and he will give the last 2. And so the aim of this first talk is to explain what a pseudo-reductive group is and why one should care, and just some basic features of them. So everything in these lectures is joint work with Gopal Prasad and Ofer Gaber. And I should say that the main goal, in some sense, is to develop. So we want a sort of a theory for algebraic groups. So whenever I say algebraic group, I'll mean linear algebraic group in the sense that was discussed in the previous talk, or in other words, a smooth affine group. So develop a theory for algebraic groups over general fields replacing the role of reductive groups. So I'll explain what I mean by this. I'll clarify what I mean. So if you want to study certain questions about general linear algebraic groups over many interesting fields, it's possible to reduce problems to this class of reductive groups that I'll review briefly, which have a very rich internal structure theory. But over wider class of fields, it's not possible to do that, and the theory of pseudo-reductive groups is meant as a kind of replacement for this. So let me start with some examples. So these are going to be examples of reductive groups. So one has classical examples, so like SLN, as mentioned in the previous talk. Also unitary groups. So here, K is going to be my general field. So general field K. So if K prime over K is a quadratic Galois extension, then you can make a special unitary group, much as you do in the special case of the complex numbers over the real numbers, and you can imitate that. And so this is one basic class of algebraic groups. One can think about symplectic groups. Special orthogonal groups. So special orthogonal groups, or more generally, orthogonal groups where maybe VQ is some non-degenerate quadratic space. Okay, so this could be your finite dimensional vector space over K. And this could be a quadratic form. So if you're like not in characteristic 2, this maybe could be, for example, sum of squares. And then we consider the orthogonal transformations that preserve the quadratic form. And then there are variations of these. So various kinds of automorphisms of interesting algebraic structures. And then in the opposite direction, so these are highly non-commutative. So these are in some sense very non-commutative. And then in the commutative direction, well, in Brion's lecture, he mentioned so you have GM, and you can take powers of GM. And let me just say twisted versions. Of powers of GM. And a basic example would be if L over K is a finite extension of fields, which is separable, then roughly speaking, if we think about L star as an algebraic group over K, so roughly speaking, if you write L as a K algebra and you choose a basis and you express the algebra structure in terms of structure constants, then the condition of being a unit can be expressed in terms of the field norm, and that's given by some polynomial condition. Okay? So groups of units of separable field extensions give you twisted versions of this. So these we call tori. This is called a torus. Okay? So these are the basic classes of reductive groups. And just before I get to the actual definition, let me just state a fact. So in characteristic 0, if G is a connected linear algebraic group, so for the entire talk, G, if I don't say otherwise, when I write G, I'll always mean a connected linear algebraic group over K. If this acts algebraically on a finite dimensional K vector space V, then the action is completely reducible. V is built up as a direct sum of some VI, and these are G-stable and irreducible. Okay? So in characteristic 0, every representation, if and only if, sorry. So in characteristic 0, if I give you a linear algebraic group and you act algebraically, then it breaks up as a direct sum for all such actions if and only if G has no non-trivial connected unipotent normal K subgroup. So by unipotent, I mean a normal subgroup, so U in G, where all points of U geometrically are given by unipotent matrices. So as Brion mentioned in his talk, any linear algebraic group you could think of faithfully represented in terms of matrices, and then an element we'll call unipotent when it looks unipotent in one and then equivalently any matrix representation. And if you have a non-trivial connected unipotent normal subgroup, that's an obstruction to completely reducible representation theory. And in characteristic 0, that's the only obstruction. Okay? So these are the things that we want to avoid. And so we'll give that a name. So maybe I'll... I can't move that. OK, so should I start at the front? OK. So let's move over here. OK, so let's give this a name. So definition. So the K unipotent radical RUKG inside G. This is the maximal smooth connected unipotent normal K subgroup. Okay, so everything is being done over K. So the simplest example would be if G is some group of upper triangular matrices with various size blocks, and then inside of here you look at the subgroup where you put the identity matrix on these blocks, leave 0 here, and leave this arbitrary. So this would be the K unipotent radical. Okay? And then we'll call G reductive if this is trivial over K bar. Okay? So this is a purely geometric definition. So you start with your group, which might be given by some conditions over K, like if the quadratic form is given over K, preserving it is given by polynomial conditions over K. But I'll call the group reductive if, even after you go up to algebraically closed extension, you still can't find any of these connected unipotent normal subgroups that are non-trivial. Okay? So that's this property of reductivity. And so, for example, as we saw over here, so in characteristic 0, this is actually turns out to be the same. Well, let me make a so remark. So if K is perfect, then by Galois theory, the unipotent radical over K actually accounts for the entire unipotent radical over K bar. So in principle, you could imagine that if you allow yourself a bigger field, that you might have more interesting unipotent normal subgroups to play with, and then you have the maximal one. And as long as the field is perfect, then the maximal one automatically descends to be defined over the ground field. So over perfect fields, there's not really a difference between the triviality of the geometric version and the triviality of the original version. And in particular, if you're working over a finite field or a field of characteristic 0, then there's not a tremendous difference between studying this geometric version versus this sort of k-rational version. And so let me now make the definition. So we'll say that G is pseudoreductive if this incarnation over K is trivial. Okay? All right. And so the two things that need to be conveyed are why this is a sort of, so this is an extremely interesting class of groups. These guys have a very rich structure theory. And it includes all of these cases here. Okay? So just as Brion had mentioned in his lecture that when one classifies the finite simple groups, so I remember when I was a student and I heard about the classification of finite simple groups for the first time, it sounded kind of horrifying because although you had these 5 infinite families, unless there was some systematic way to actually study them all in the same manner, it just sounds like, okay, you have this infinite collection of groups. Okay? But you see, the beauty of it is that although you have these different classes of examples varying the quadratic forms and varying these fields, that from a certain viewpoint, one can study all of these reductive groups by a kind of common technique. Okay? And so once you know that an algebraic group fits into this class of reductive groups, then there's a sort of body of methods that you can use to study their internal structure theory in a systematic way without having to make lots of case-by-case arguments for every single possibility. Okay? So these guys are extremely tractable. And so what I need to convince you of is, first of all, to show you some examples that this condition really is much weaker. All right? That at least if you're not over a perfect field, this can really be trivial, and this can be very, very non-trivial. And yet, to show that actually there's still something reasonable that can be said for this class of examples. So just a couple of facts. So first of all, reductivity is a very robust notion. So for example, it's preserved by connected normal subgroups, closed normal subgroups, and quotients. And this is not obvious from the definition, but it's true. So reductivity is a very good notion. And also, if you compute centralizers, it's often preserved when you take centralizers of certain interesting subgroups. So here I mentioned the tori. So in the commutative setting, you get exactly the tori. So commutative, so reductive plus commutative is the same thing as being a torus. So in the context of reductive groups, the commutative objects are completely under control. These are these tori, which are just twisted versions of this. And these have extremely simple representation theory that's very easy to make explicit. So it's quite tractable. And inside of reductive groups, if you have a torus inside of a reductive group, their centralizers are again reductive. So if G is reductive, and S, I'll do an example in a moment, S in G is a torus sitting inside, then the centralizer is again connected and reductive. So one can make very nice inductive arguments by passing to torus centralizers. So for example, if G is something like, say, SL3, and S consists of matrices t, t, t to the minus 2, then the centralizer is a copy of, is basically a GL2. And then down here, you just have the inverse determinant to make the whole thing. So it's just GL2 with the determinant down there to make the whole thing have determinant 1. Okay? So reductivity, if you take certain centralizers, quotients, and so forth, reductivity is preserved, and yet they have a very good internal structure theory. Okay, but now I need to convince you that this is really a strictly weaker condition, and also to show you by means of examples why you would be interested in studying this weaker condition. So let me give you, so the kind of most basic non-trivial class of examples of this would be the following. So I start with my field K, and let me assume that it is not perfect. So I have my field K, and I have some finite extension. And up here, suppose I give you some G prime, which will be a reductive group. Okay? So this is over K prime. All right, so maybe this is the real numbers, this is the complex numbers, or this is some interesting function field, and this is some non-trivial finite extension. Then, well, you can always form what's called the Weil restriction. So this is roughly speaking, think about G prime, so it's called maybe G prime as a K group. So what do I mean by that? Well, so in differential geometry, you can take a complex manifold of dimension 7, and you can view it as a real manifold of dimension 14. You simply take every complex coordinate z, and you write it as x plus iy, and you get twice as many real coordinates. Okay, so somehow the dimension goes up by a factor of 2. Well, similarly here, if you have an algebraic variety given over some field extension, and maybe this is smooth of some dimension d, you write this extension in terms of a basis over this, in the same way that C is R plus Ri. Okay? So you write this in terms of a K basis, and you express the algebra structure in terms of some structure constants for that basis. And then the algebraic equations that describe this group over K prime become this degrees time as many equations over this, in the same way that equations over C become many more equations over the reals. Okay? So in that way, for any affine variety over this big field, you can turn it into, in some sense, a variety over this smaller field by rewriting the equations over K prime in terms of the equations over K. But a fundamental difference between the differential geometry situation and the algebraic geometry situation is that in differential geometry, the underlying space is the same. You're just describing it in terms of real coordinates, but it's literally the same space. Here, this is really a different algebraic variety, although the equations that define it and the rational points of this correspond to the equations of this over this field, and the K points of this correspond to the K prime points of that, just like the real points of the underlying real manifold or the complex points of the corresponding complex manifold. So in this setting, if you start with something smooth, let's say this is finite of degree d, then this guy here will be smooth, connected affine variety of dimension equal to the dimension of G prime times the field degree. Okay, so what? But I claim that actually this can fail to be reductive. Okay, so fact. So if K prime over K is not separable, and G prime is a non-trivial reductive group, then in fact, this guy is never reductive. So let me explain that with an example. On the flip side, when this is separable, this actually is always going to be reductive. So what goes wrong? So let me just illustrate this with a simple example. So let's suppose that we look at a degree p extension. So alpha to the p is equal to some a, which is not a p-th power. Right? So this is not a perfect field. Let's say this is an inseparable extension. Okay. Now, what happens if, let me call this thing G. So what are the points of G geometrically? Okay? Well, it turns out those are exactly the points of G prime with coordinates in the scalar extension. Okay? But if you write this, right, as a quotient of, k bracket x, so this guy here you can think of as k bracket t mod t to the p minus a. But over k bar, you can rewrite this as k bar bracket x mod x to the p, where x is the t minus alpha. Okay? So although this guy is irreducible over k bar, when we extend scalars, we can additively translate the parameter, and then it looks like this little nilpotent ring. But now this, you can do reduction onto g prime of k bar by sending x to 0. Okay? So this maps onto the original group. And then there's a massive kernel that comes from matrices which have sort of nilpotent entries. Okay? But all of that stuff, when you raise it to a big p power, will wipe out. This has a huge unipotent kernel. Okay? And that contradicts the possibility to be reductive. Okay? So this group G, geometrically, it has a massive unipotent radical coming from the kernel of this reduction map. Okay? But we're using, crucially, that this field extension was not separable. All right? So on the other hand, but such G is always pseudoreductive. Okay? So that's not obvious, but in the interest of time, I'm not going to give the proof here. It follows from basically a direct application of the universal mapping property of the Weil restriction when you express it in the correct way. But I can explain that afterwards to anybody who's interested. So if you take Weil restriction through a kind of bad field extension, reductive does become pseudo-reductive. Okay? But more importantly, if you use a kind of bad field extension, then in some sense geometrically there's going to be this huge unipotent radical, but you can't see it over the ground field. If you only allow yourself to work with subvarieties defined over the ground field, you don't detect the presence of that geometric unipotent radical. Okay. So that's a basic example, and if every example were of this form, then that would be great. But part of the interest of the theory is that there are many examples that are not. provided the characteristic of K is not 2 or 3. Okay? On the other hand, in characteristics 2 and 3, there are more exotic phenomena. So if the characteristic of K is 2 or 3, then more exotic phenomena occur. And we want to explain those. Okay, so we want to account for these also. Okay, so in Prasad's lectures, so I'll explain what the standard construction is next time. And so Gopal will say, well, he'll say a variety of things, among which will be to discuss why this standard construction, to be explained next time, does account for everything away from certain characteristics, and to give some flavor of the zoo of things that can happen, especially in characteristic 2, and how one can nonetheless get a handle on those as well. So there really are two separate things. This kind of internal structure theory is completely characteristic free. It doesn't really go characteristics 2 and 3. But then in terms of making explicit constructions that realize everything, then the peculiar phenomena of small characteristics, certain things come up, and those have to be accounted for. Okay, so in the last 5 minutes of the talk, or last 10 minutes of the talk, I want to say a bit about some positive things that one can say without a lot of preliminary work, just to convince you that these pseudo-reductive groups do have some reasonable properties. So far, I've shown you that at least I've told you that it's not preserved, for example, under reasonable quotients. So I want to tell you some positive properties to make it hopeful that there is some reasonable theory to be developed. But before discussing that, I want to give as an illustration of the utility of this sort of stuff, I want to state a finiteness theorem whose proof actually rests crucially on essentially everything in the sense of both the internal structure theory as well as this ubiquity of the standard construction and an understanding in low characteristics of what other things can happen. So let me now digress and discuss a kind of finiteness application. So here's the problem, and it's going to be somewhat in the spirit of the setup of this example down here. So let me first state, actually, here's a general principle. So maybe I won't write it, I'll just say it. So the general principle is that if you have a problem you're trying to study that involves a possibly quite general linear algebraic group, and if you can solve the problem for reductive groups and for unipotent groups, then by one way or another, one should be able to use this, which in characteristic 0 would basically tend to solve the problem in general. But if you're over an imperfect field, then the pseudo-reductive structure theory should enable you to sort of solve the problem in general as well. Okay, so let me set up the basic finiteness application. So suppose X is a smooth quasi-projective variety, could be affine, for example, over K, and I have an action on it by G, which will be a linear algebraic group, so a smooth affine group over K. The smoothness is not relevant, but it's perfectly interesting already for what I'm about to say. Okay, and what I want to ask, so for example, X could be the space of non-degenerate quadratic forms in 5 variables, and G could be GL5 acting on that through linear change of coordinates. Okay? And what you want to ask yourself is, if I give you 2 rational points here, how can I detect when they are in the same orbit under the rational points of the group? So I'm going to take K here to be a global field. So it could be, for example, the rational numbers, or maybe function field over a finite field. And I give you a point x0 in X over K. And now, for any other point X, rational over k. I want to know whether I can get to it from x naught, provided I pass some local tests. So can we detect if x is in the k orbit of x naught using local calculations? All right, so what do I mean by that? So since we're working, for example, if we're working over Q by local calculation, what I mean is let's test it by working over the completions of Q at all the different primes. So we can check over the reals or check over its various p-adic completions. And usually in these kinds of arithmetic problems, there are some primes that are pretty bad for what we're trying to study. So maybe we'll ignore finitely many of those. So let's fix a finite set S of places of K. And let's assume that X is in the local orbit under the completion everywhere away from that finite set of places. Okay? And then the question is, does this imply that X is in the global orbit at least up to a finite discrepancy? Okay? So let's consider the set of all such X. So X in here that pass the local test away from that finite set of places. And let's consider those points up to the K orbit, and we ask if this is finite or not. Okay? In very classical situations, this might even be the trivial set, when S is empty, for instance. Anyway, so this is the basic finiteness question that one can ask. And let me just say that after some relatively standard procedures, this reduces to the finiteness of what's called the Tate-Shafarevich set relative to S, but for the group given by the stabilizer of the point x naught. Okay? So this is the set. If I call this stabilizer G, this is the set of G torsors over K, which have a rational point everywhere outside S, considered up to isomorphism. Okay? So this is so the problem, which originally involved the group G acting on the space X, now it's really a question about the stabilizer. All right? Now this stabilizer could be pretty bad. It might not be smooth, or as we saw in the example, what was the example with the Weil restriction? It was on what I just erased. This could be maybe smooth but not reductive. Okay? Well, okay, so it turns out by a trick, you can replace this with the maximal smooth subgroup, which I should just warn you, of course, if this is reduced, it might not be smooth. This could be very small inside. And the thing I want to stress is, even if G is a very nice concrete group, if we really want to handle all points on equal footing, in general, maybe we don't know what the stabilizers are. And if some of those are not smooth, the maximal smooth subgroup, it's not clear what structure it can be. So this is a kind of example of what I was alluding to at the beginning, that it's just some group, and in general, one knows very little about what it can be. Okay? And so the problem of this finiteness really reduces to this question is of, if H is a linear algebraic group like this over that field K, so is the Tate-Shafarevich set finite? All right, and the answer is yes. In characteristic 0, this is a theorem of Borel and Serre, but one immediately reduces to the reductive case, and then they sort of analyze that using everything that one knows about the arithmetic properties of semi-simple groups. And in characteristic P, well, this was solved by Harder in the reductive case, and much easier is the the solvable case or the unipotent case by Oesterle. And the question, but getting beyond that, not so clear. Okay? And then what you want to do is bootstrap to the general case by using the structure theory of pseudoreductive groups. Okay? So in the end, one gets an affirmative answer, but to do that, one needs to know the ubiquity of this standard construction, as well as how to work with that in analyzing things like the Tate-Shafarevich set. Okay, so let me end by telling you a few positive properties. So far, I've just illustrated that, okay, you might start with a problem with a reasonably nice group, and if you don't want to make any hypotheses on the stabilizer, then you have to answer this question for quite general groups. And we saw that a general group can be related to a pseudoreductive group quite easily, but that's only useful insofar as these pseudoreductive groups have some reasonable properties. Excuse me, and in order to establish those properties, a priori it might look kind of hopeless because I already noted that this property is not preserved by quotients. Okay, so it's not nearly as robust as in the reductive case. So let me just end by pointing out, well, tell you something I'll call the magic lemma, which at least at the very beginning of the theory allows you to bootstrap some non-trivial properties of reductive groups to the general case, but it's really just the very beginning of the story, but at least it'll give you some flavor that there's something reasonable that can be said. So some good news. Okay, so given that the pseudoreductive groups don't seem to have such robust properties, how do you get a handle on them? Okay, so I'll call this the magic